So we have been talking about functions, and remember we talked about that I gave this easy bake oven analogy of what a function is. It can be thought of as some machine, something goes in the machine, some magic happens, and then something is spit out of the machine. And the set that holds all the things that can go into the machine or the function, we call this the domain. The set of possible outputs from a function, we call this the codomain. And remember, there was a difference between the codomain and the range. The range is the set of the actual outputs of a function. And I'll give you an example in 1 second to help you to distinguish the difference. In this class in particular, we are working with sets, the domain, codomain. There may be restrictions on them, of course, but we're talking about real numbers in this class. So some of the functions we looked at, for example, polynomials, a second-degree polynomial or a quadratic function or a parabola, all those terms are used interchangeably. We saw that depending on the coefficients for your parabola, we could get complex values. Mathematically, it's not a problem, but in the sets that we're interested in, we don't want those types of solutions. Okay, so sets, you can have a variety of them, but in this class, we'll be working over the reals. And in terms of vocabulary, so we have these sets A and B, which we think about to be R, but I'm writing them as A and B so we can more easily talk about them. And a function is a rule that takes each element from our domain and gives one f of a. Remember, sometimes we rename it to be b or we rename it to be y for convenience. And sometimes that output, that f of a, it's referred to as the image under f. Okay, so that's just special vocabulary. And when we put this a through our function, in terms again of vocabulary, we say that f is being applied to this element from our domain. Okay, so just for those who haven't heard that vocabulary, f being applied to a function means that I put this a through f and it spits out something called an image or an element in the range. Okay, means the same thing. And in terms of a definition, the set A is called the domain and consists of all the elements that f can be applied to. So in other words, can go into our function. And the set of all outputs or images of a function is called the range. Is give you an example of a function to help you better understand the range and the codomain. So let's say that we have a function, f of x, and we'll state what its definition is in a moment, but it's a function that's going to take things from real numbers and it's going to map them or send them over to another set, which is real numbers. And the rule or the formula or how the function is defined is by f being applied to x and it spits out x squared. Okay? And let's say, for instance, that we consider x being equal to 1. Okay, so if x is equal to 1, that means if I apply f to that element, I replace my x with it, I'm going to get 1 squared, which is just 1. If I instead consider x is equal to -1, and I apply f to -1, it's going to give me -1 times -1, which is also just equal to +1. So what types of numbers will I always get from this function? If I put in 2, I would get 4. If I get -2, I also will end up getting +4. So our domain is the set of all real numbers. Okay, there's no restrictions. And what I mean by that is I'm not seeing anything with a square root, or I'm not seeing anything that has a denominator. Those are the types of functions that will have restriction. So I'm not seeing anything like that. So my domain is all of R. My range, in this case, the types of answers I get out, these are positive reals. Okay, so this means positive reals, which does include 0. 0 is fine. So positive reals. But my codomain, this is R, the thing that I'm told in my question. So for this example, my codomain and my range, these are not equal to each other. It's almost like, pretend the codomain is your parents' house. Maybe your parents have, you're not allowed in their bedroom, for example. So the range should be every room that you're allowed into, but you can't go into their bedroom. So the entire house, what you have access to, is not equal to what you're allowed to go into. How do we express the domain and range? When you're talking about a set is a type of number system, or depending how a number is expressed, we put it into a certain group or a numerical system, which is called a set. So in my head, typically when I think of a set, I think about a house or a big bubble that contains certain mathematical objects. Okay, so a set basically contains certain types of numbers or certain types of elements that all follow certain rules. Natural numbers, this set, we give it a special name because in math, we refer to it a lot. Okay, typically we just name it this fancy n. What is it equal to? The set of natural numbers has things like 1, 2, 3, 4. They're basically positive integers that do not include 0. And whenever we define a set, we use these squiggly brackets. Another example of a set that has a special name is the integers. Okay, we use this fancy Z here. And if you wanted to write it out explicitly, typically we write it like this. And the ... means that you keep going. You go on to infinity. I'm not going to write out infinitely many numbers. I'll literally be here forever. Another thing is rational numbers. Okay, this is just more to show you further examples. The important one is rational numbers, this fancy Q. And what are those? They're fractions. And what are fractions? Fractions are when you have an integer over another integer where your denominator is not equal to 0. And this is another way we can express a set. So we can either write down elements or we can write down the rule. Irrational numbers. Okay, in terms of notation, they put a bar over it. That's set theory notation. Don't worry about it too much. But this is all the numbers that have infinitely many decimal places. And then the real numbers, the reason why I wanted to mention these was because we talked about real numbers include rational numbers and irrational numbers. And rational numbers also include integers. So for us, real numbers is basically anything that doesn't have an I in it and that's some sort of number. Here's just a little picture to show you the connection between all these things. So find the domain of the following function. So this is an example of a function that we are going to have restrictions. How do I know that? Well, first of all, what type of function is this? This is a rational function. We have a denominator, and we can't have the denominator being equal to 0 because otherwise our function is not defined. We will have restrictions. We will have restrictions because of the square root and because of the denominator. Okay, so let's start off with the square root. Okay, so let's do the square root part first. X plus 2, the square root of it, this cannot be less than 0. Or another way you can think about writing this is the square root of x plus 2 has to be greater than 0, or it could be equal. Don't forget the equal. Okay, so it can be equal to 0, because if you have 0 on your top here, that's not a problem, because 0 over a number is just 0. Okay, so let me write down here so we hopefully don't forget. 0 over a number is just equal to 0. This is okay. That's not a problem. Okay, and if you're ever unsure in the moment, if you forget, put it in your calculator. Go 0 over 2 and see if your calculator goes or if it's okay. So now I want to isolate for my x, and now I'm working with these inequalities here, but don't let them trip you out. So I can think about taking squared of this whole expression. We technically don't even have to write the square root there, but I'm just doing it to give you extra practice. And then I have to have x plus 2 greater or equal to 0. So to isolate for my x, I'm just going to bring this over to the other side. And I get x is greater or equal to -2. If I wanted to write this in interval notation, greater than -2, so at the bottom here I have a -2, But greater means like 0, 1, 2, 3, 4, infinity. And infinity always has, for the denominator, the x squared plus 3x part. What's the restriction here? What don't I want?
We don't want a 0.
Right. So we don't want x3 plus 3x is equal to 0. It's not allowed. What I can do is I can factor out an x. So then I have x squared plus 3 here. Cannot be equal to 0. And now we're going to look at each of these terms separately because these are being multiplied. So this means two separate things. Number one, x cannot be equal to 0. So 0 in this interval right here, I would have to split up my interval again because I don't want to include 0 in it. Okay, and then this second part here, this x squared plus 3 cannot be equal to 0. That's also a restriction I have. X squared cannot be equal to -3, but is that allowed? No, it's imaginary. So this isn't even in our domain or codomain. Our function can't even have imaginary values. So this situation here, this does not apply to us. So even though we have that term on the denominator, it's not going to influence anything in our case. For this part, the denominator part, it's like you have to split it up. You literally have to break it. So I'm going to go from -infinity to 0, not including 0. So this is an open interval, open brackets. And then not including 0 to infinity, those are okay. And if I put these together, union or, whatever you'd like to think about it, because this is giving us a little bit of contradictory information, right? This is everything but 0, but this one up here is saying -2 to infinity. So -2, that's including that, right? To 0, not including 0, so open bracket. And then we're going to do the big U here. And then everything above 0, not including 0, is fine. So we have this. Okay? Now, because unions, in terms of notation, when you have a union, this is actually a type of set. So because it's a type of set, you don't have to put the squiggly brackets there. For these graphs, so there's also some additional information here. If you have some sort of f of x is equal to something, but the x that you put in is a negative value, and then when you apply f to that value, you can write your formula f of x and then put a negative out front. That's an odd. So for example, if you had f of x is equal to x cubed, and you put in f of -x, I'm going to get -x all cubed, but that 3 distributes to both the -1 and the x, and -1 to the power of 3, -1 times -1 times -1 is negative, so we can write this as -x cubed or -f of x. Okay, an even function is when you put in a negative and you still get the same thing out. Okay, so again, don't worry about this too much for now. We're going to be formally defining this and working with this in a little bit. But if you have f of -x and you get your same function back, that's even. So an example of this one could be a standard parabola, where if you have f of x is equal to x squared, and then you put in your negative, you're going to get -x squared, which is just x squared, which is f of x. So don't worry about this part for now, the odd or even, but get you to start looking at it a little bit. So for this function, this is a linear function, or the equation of a line, or a first degree order polynomial. Okay, they all mean the same thing. And these graphs here also state what the domain and range is. So graphically, sometimes it's easier to see what the domain and range is. And how you do that is you look across the x-axis and see basically if you always have an x value corresponding to it. So here, I don't see any issues where I can't have an x value. I don't see any vertical asymptotes, for example. And I can say then my domain is -infinity to +infinity. Now, my range, look to see along your y-axis. Are there any y's that you're not allowed to have somewhere? And again, here there isn't. There's nothing odd happening here. So we would say that the output, the types of y's we can get, are all real numbers. Quadratic. This is also an example of a polynomial. So actually, let me write down here really quickly. So this is a polynomial. That's the class of functions that we learned about. This is also a polynomial. This is a second degree quadratic or parabola, all these interchangeable names. And for this one, we don't have any restrictions on what x can be here. I'm not seeing square roots, I'm not seeing denominators, but I do have a restriction on my outputs. Okay, notice that if you were to take a pen and you tried to look along these y values, I don't see anything there. So my range in this case would only be positive values, including 0. Okay, cubic. This is another example of a polynomial, okay, where we only have the third order term. And this would be odd again because of that power of 3. And we don't see any issues with x, okay, no vertical asymptotes, and I'm not seeing any issues with y. So our domain and our range are both all real numbers. Okay, this was an exponential function. And this one is neither even or odd for those of you who know what that is. Okay, there's no mirror image anywhere. This is exponential. And remember, exponential functions, we have no problems putting in x values. Okay, we can put in any x, but for my range, again, I'm not going to be getting any negative values. Okay, so here, I'm not including 0 either. Okay, because as x gets really, really negative, we get really, really close to 0, but we never actually hit 0. Okay, so this is our range in this case. So the inverse of 1 over x, sometimes it's called, but for how we define these things, this is a rational function because it's an example of a polynomial, just a constant polynomial, over a polynomial which is just a linear polynomial. Okay, now for this one, we did look at this one in class, our 1 over x here. Remember that this one, we have something in the first quadrant and the third quadrant, okay, and they're actually mirror images of each other. But I don't have anything here and I don't have anything here. And the other thing is that my bottom can't be equal to 0. So I have a vertical asymptote here. So meaning when I'm going along my x, oh, I can't go here, but everything afterwards is fine. So for my domain, I have to split it up. I have to get rid of my 0. So that's why it looks like this. And then for my range, the range is the same thing. I'm actually getting all my values of y and all my values of y. Okay, I'm seeing the lines here and here, but I'm never actually getting it at 0. Okay, so my range is this. Don't worry about this one. Okay, we are, at least, I don't think we're doing this at all in this class. Okay, this is something that the math students do, but don't worry about that one. So the absolute value function, the best way that I personally, or not the best way, a way that I think about it is that the thing inside the brackets here, if you were to graph that, okay, it would just be this line, right? It's just y is equal to x. So when you have an absolute value, everything that's below the y-axis, everything below, y is equal to 0, you have to flip it up here. So instead of negative, it becomes positive. So it's a mirror image about this axis right here. So you would just redraw it up there. Now, our domain and range for this. So the domain, as you can see here, we have no problems with x, but whenever we get things that would be negative, so if we had y is equal to x, we always flip them to be positive. We flip them about the x-axis. We'll talk about that one later, so don't worry about that one too much. So the root of x. So this is an example of a radical because we have a square root. Okay, and for when we have square roots, remember that those values, the types of x's we can put in them, they have to be positive because we're not allowed to have negative root values. So both the domain and the range, they have to be positive, but they can include 0. Okay, so we have our domain and range right here. The cubic root is another example. Now this is also a radical, but we have to be a little bit more careful because remember when we have radicals, we think about it, what times 3 is going to give us our x. So when you have odd radicals, odd numbers here, so like 1, 3, 5, 7, so on and so forth, you can have things happening in the negative x-axis and negative y-axis. It's when it's even that it's a problem. So the cubed root, if you were to plot it out in some software on your own, it would look like this. And there's no restriction on what the domain and range can be. For the logs, we have our range, the types of outputs we can have, the types of y's. There's no restriction on that. Okay, so we typically just look at it from this point, but if you get x's between 0 and 1, your y just becomes more and more negative. Okay, it's a vertical asymptote basically. But our domain, the types of x's that we can put in cannot be negative values, and it cannot be equal to 0. Okay, so there's our domain and range there. This is another example of a rational function, okay, 1 over x squared. So in this case, our denominator can't be 0. So in other words, x can't be 0. We have vertical asymptote right here. Okay, so our domain then, everything's fine except 0. And for our range, if we were to plot this, it's always above the x-axis. Okay, so this is what our range would be. And again, this is an example of a rational function. We have a polynomial divided by a polynomial. Technically, this is a polynomial. Okay, this is a constant polynomial. Okay, and it just looks like this. Now, our domain here, okay, we can have any x value. So we have x values all along here, but our range y, that's only equal to one value. And to easily write that in set notation, that's what they're doing here. And these dots here, by the way, this just means such that. And really, what they should be saying is they should be saying y is an element of R, such that y is equal to c. Okay, so here's a summary of all of our trig functions. We have our sine, we have our cosine, our tangent, our cotangent, cosecant, and our secant. And our sine looks like this. And remember, sine and cosine, they're in between whatever the coefficient is in front of them. So if we just have sine or cosine, they're going between -1 and +1. So their range is only within here. But their domain, they can go across any x. Okay, so that's true for both sine and cosine. Tangent, this looks a tiny bit awkward. So for the range here, tangent looks like this. So I have no issues with y values, but remember, tangent had these asymptotes, these periodic or cyclic asymptotes that happen. They happen at pi/2, and then they happen in intervals of plus pi. So they happen in factors of pi/2. So the domain can be any real number, not including these. These trig functions on this side are 1 over these ones. So whenever you have zeros on the left-hand side, they're going to correspond to asymptotes on the right-hand side. Okay, these are the ones that are more important for you to know right here.